Hi, everybody. Welcome. My name is Bo Dagnall. I'm the Chief Product Officer for Smile Digital Health, and I'm joined on stage by my colleague, Brian Carlsen.
Hello, everybody. I'm Brian Carlsen from West Coast Informatics. We're going to be focusing today on semantic normalization to improve digital healthcare. So the current state of the world is that data exists in a lot of different places and in a lot of different forms. For real clinical care scenarios, often you have to pull data from multiple EHRs, lab systems, pharmacy systems, and you get data that comes in a lot of different forms. And it can be CCDAs or FHIR data, unstructured notes, PDFs, all sorts of things. Some of this data is structured, some of it's semi-structured, some of it's not structured at all. And when you're attempting to compose a longitudinal record for patients, this leads to a fractured and incomplete view of the data. This is a problem because it makes it harder to answer questions, to find patients for different scenarios, and to deliver better outcomes. What's needed here is both syntactic standardization of the incoming data to put it all in the same form so you can treat the same kinds of things the same way, and then also semantic standardization to kind of harmonize the meaning of those records. So when you're talking about a condition or a medication, you know that you're talking about the same thing. And this is the case for healthcare data at large, but then that means it's also true for individual patients. So meet our patient Avery, has a family history of colorectal cancer, is of a certain age, has a number of comorbidities, is on a few medications, and has a history of recent lab tests. Our goal here is to achieve a level of data quality so that we can enable analysis that's informed to be able to do things like find care gaps or treat, better treatment options for Avery. You'll see here there's boxes with words in them. Semantic standardization is syntactic standardization is about getting all of the data in the right kinds of boxes, putting conditions and medications and lab tests together. And semantic normalization is about transforming all of the data to standard terminology codes. So words are good for people and doctors to interact with and make decisions about care, but when you want digital health applications, it's really much better to have coded representations that carry that meaning forward. So things like SNOMED for RxNorm, LOINC for labs, SNOMED, RxNorm, and LOINC to represent the things. And that allows computers to be able to process the data in a more effective manner.
Thank you, Brian. And this is really important for our customer, our patient Avery, because Avery has clinical data that might be indicative of colon cancer. She has a family history. Both her father and her maternal aunt were diagnosed with colon cancer in her 60s. She's almost 60 herself. She has certain lab data and risk factors like Crohn's disease that might be indicative of colon cancer. So we want to identify patients like Avery so that we can intervene. And this is a big deal because colon cancer is the fourth most common cancer in the United States, with over 150,000 people being affected in 2023. A third of those, 50,000 people, actually died from colon cancer. And the important thing is that we can do better. We can intervene. We can screen for patients. We can identify patients who have gaps in their care. And we can reduce the deaths by up to a third. But how do we do this? How do we effectively find Avery amongst all the people with all of this data? Well, one way you do that is you write queries for screening. And what we're showing you on the screen is a snippet of CQL, or the clinical quality language, a standard for defining clinical logic and criteria. And as you can see on the screen, what we're trying to do is just a snippet of the criteria, looking for a family history for Avery, for someone who might have had colon cancer diagnosed. But the problem is that the term colon cancer can be expressed so many different ways. When you look across all the medical records, you'll see different variations of lexical variants or misspellings or acronyms of all saying the same thing or similar concepts. And so if you're trying to write a query to find patients who might be a candidate for screening, you've got to account for all of these possible variations. And you can see there's like 10 or 12 different flavors of colon cancer, all with different ICD-10 codes or SNOMED codes. And if you're a very good clinical query language author, you would write a very robust, comprehensive query like this. But even at the end of it, you'd still miss some, right? Because you can't account for all possibilities. So we show you in the bottom right there, or bottom right from your perspective, that there are a couple of additional codes that this particular query left out. So you get false negatives, right? So it's cumbersome for the knowledge engineer to write these queries. It's also inaccurate with these false negatives, right? We can do better than that. And this is just part of the problem. We're just showing you an example with family history, right? This problem is compounded when you look at lab results and common procedures and demographics and comorbidities. All of this will suffer from the same problem, and the query becomes very large and very hard to manage, right? We can do better. If we were able to standardize the data, the query might look something more like this: more concise, more accurate. We can look just for the code for the concept that's been standardized. In this case, the SNOMED code for, I can't read it, but the colon cancer SNOMED code. And we can be assured that when we run this query, because we standardized all the medical data, we're going to catch Avery. And whatever was in her original record, whatever way that was expressed, that's going to be found and mapped to this common concept. So when we write the query against a common concept, we're now going to find her within this population of people. And that's what we're trying to achieve here. And at Smile Digital Health, we have a very robust vision for how to implement these types of solutions across a very end-to-end and complete data ingestion pipeline. It all starts with connecting to the data sources themselves. As Brian called out, this could be multiple different EMRs or proprietary databases, HIEs, you name it. Each one has data in a different data model. Each one is accessed through different APIs and access mechanisms with varying degrees of standardization. You've got to meet your customer where they're at, which means you're going to work with this. And what you get out of this is effectively a dust cloud, if you will, as shown in the picture. Think of Linus from Charlie Brown. I think it's Linus. And in that dust cloud is some key data elements, right? The lab results are there, the comorbidities are there, some of the demographics, but it's hard to work with. You can't write queries against this dust cloud, even though the data is there. A human can understand it, but a computer cannot, right? So the first thing you need to do, you need to break this apart. You need to start parsing this out into standard representations using standards like FHIR. So the first step here is to do exactly that. Apply some mapping logic, do a transformation, and pull all this information into FHIR resources. Once you've done that, you've sort of compartmentalized it. It's easier to work with now. You can understand it. You'll see there are patient resources, there are condition resources, observation, family history, medication, et cetera. It's all sort of organized and cataloged neatly in a FHIR standard now. But we're not completely solving the problem because the data itself is still text. It's still words. And as Brian pointed out, you can't reason against words very well. And there's so many different ways to say the same thing within the medical lexicon. So the next step is to standardize this now semantically. And by that we mean map this to medical terminologies. Things like SNOMED, things like ICD-10 or LOINC, RxNorm, and you've heard of these things. Traditionally, this is done by humans, experts, terminologists who understand data and understand the coding system and do the work to create those physical mappings, right? We want to do this at scale, so the data inside the FHIR resources now have the appropriate codes that we can now write clinical language and clinical queries against and have assurance that the data quality matches our need. And then the last step in this journey is that we want to validate this data against a set of rules, data quality rules, because even after you've standardized it, you're still going to have additional problems like perhaps the family history resource is missing the reference to the person in their family who had the colon cancer, like their father or their maternal aunt, or perhaps a drug doesn't have dose or frequency. And the talk of today is not about this thing, but I would encourage you guys to learn about PICI, and I see Charlie Harps in the crowd over there. There's a new emerging standard about data quality framework that addresses exactly this problem. But today's talk is about semantic standardization, colored here in yellow. Like I said, this is not new and novel. People have been working with medical terminologies for quite some time. But what we're bringing to the table that is new and novel is we're doing it with AI. We're automating this solution so we can do the mapping in real time at scale using AI. So with that, I'll pass it back to you, Brian.
So as Bo said, it's not like we've never approached the problem of doing semantic standardization. Just traditional approaches have involved human curation, so putting things through a pipeline that sort of uses traditional techniques to get at an answer and then having subject matter experts review all of those things. And that works at human scale, but it's very expensive and time consuming to do if you have a large amount of records and you want to get it done quickly across that scope of data. So we're taking an AI approach to all of this, and there's several dimensions to this I'm going to talk through. The first thing is AI is many things. It's for many things. There's many models. And so, to start all this process, the first thing we have to do is kind of think about what's out there and what's available. So we've built a solution that can interoperate with a large variety of different kinds of models. The ones you're familiar with that are top tier models with pay APIs, where you send your data out and get answers of super high quality. And there's the famous sort of smaller open source models of various sizes that you can run locally. In a real deployment of all of this, there are key requirements of how this can run. It has to run within a closed system so data doesn't leave. It has to run in a clustered environment that only has CPUs running. So we've made a lot of choices around being flexible about how this runs and what kind of environment it runs to meet the requirements of an actual live deployment that's doing this. And there's several things we're using models for. Generating vector embeddings in order to do kind of similarity comparisons, using LLMs to answer questions about data and sort of featureize things and do stuff like NLP to identify multiple entities within a similar or a same block of text. The most important of all these things is that we use is vector embeddings. So one of the key things in AI is these models get trained on large amounts of data and they create mathematical representations of words and sentences that allow you to use non-lexical means to identify correlations between things. This is very helpful for dealing with a lot of the stuff that happens in real world medical data, which is the presence of acronyms or misspellings or alternate ways of saying things. You know, terminologies express content in a certain way, but that's not necessarily the way it's used in actual medical records. And so by leveraging these techniques, we're able to take data and find matches as a candidate matches just in this very effective way, while coupling that with traditional approaches. The other problem with a lot of AI models is that they're not fast, especially like you've probably heard about the emerging models that do reasoning from the kind of big companies out there. And some of these models are really slow. They can take seconds or even minutes to answer the questions that you ask them. This is not a viable, scalable solution when you're operating over hundreds of thousands or millions of records. So one of the things we can do is leverage these models in a kind of batch mode and pre-compute a bunch of things so that we send a bunch of data up and we get a bunch of answers and then we can code those things to terminologies in the background. I'm talking about like the parts of conditions like body parts and morphologies and, you know, drug ingredients and whatever, you know, context words like recently diagnosed or things like that. And that way we have a kind of basis that can run at scale to answer these questions. And then we can use these data sets for this sort of thing called knowledge distillation, where you take the better answers provided by top tier models and you fine tune and train smaller models to be able to better answer those kinds of questions on the information that they were given from a higher level. So putting all this together, it lets us you know, operate in a quickly in a large scope of things and also be able to process novel content with effective results. And all of this is put together into a pipeline. So we effectively generate candidates for every situation and then rank those things with a confidence score. And then that's sort of a configurable means of saying above a certain confidence score, the output of this can be trusted as the answer and doesn't require human review. With all of that said, there's still always situations where you may want humans in the loop. There's enough ambiguity or lack of clarity about what something means that it requires somebody to look at it. But then that can be sort of fed back in to improve the future operation of the system. So we're originally hoping to do a demo today, but we're not set up to do that. So we're going to just walk through a couple of screenshots to sort of simulate the demo that we were going to do. So here's a sort of view of a tool. This is a tool that we use by SMEs on our site to sort of train and improve the model, to be able to run things through it and see what the results are and kind of change the answers and feedback information while we do this. It's also a great way of demoing what it does. So there's a few examples here from Avery's record that show you conditions and medications and the sort of family history things we were talking about. So these are things that have been run through. Data that has codes on it can be run through, and even coded data might be wrong. It might be referencing inactive codes or other things like that. And so we can sort of repair and upgrade and clean that sort of thing as well, or map from coding systems that aren't the standards to coding systems that are the standards. So we might put something in here, colon cancer. We're in this doing an example here of looking up, trying to find the right codes for the family history part of Avery's record. So colon cancer, we want to search for as a condition. And you'll see there's a kind of confidence score threshold in here. We say, only show me answers that are above the score. Now, it's important to say this is not how this works. There isn't someone opening a UI and putting a string in. There's API calls behind all of this and how it actually operates. And that's part of the doing it at scale part. And then here, just showing you that there's a kind of answer. So we get back the SNOMED code in this case for malignant neoplasm of colon, and also the corresponding ICD code. And just as a way of highlighting what's happening here, we asked for colon cancer, but the text of the answers we get are malignant neoplasm and malignant tumor of colon. So there's a lot of different ways of saying the same kinds of things. And that's really what this is about, is where those different phrases and different ways of talking about stuff mean the same thing, we can put them all together. So semantic standardization allows you to once it's all in the same form, have all of the things that are the same thing mean the same thing. So you can effectively ask and answer questions about the data.
Yeah, thank you, Brian. And just to underscore an important point, I mean, the mapping of the word or the term colon cancer to the appropriate SNOMED code by this software was through a trained AI model. A human didn't do that, right? And it can be done at scale now, even with things it's never seen before. So we may not have been trained on the word colon cancer, but it still understood it. And that's really the important and novel thing that we're doing here. And then we're putting this into our product, right? It's not just an academic thing that lives out there. We're actually productizing this and delivering it within Smile's health data platform, sometimes referred to as our clinical data repository, a Fire-based solution that's used in the industry. Our platform is very mature and robust. It can handle ingesting data from multiple different sources, stores it in a large database based on the Fire standard, serves it up through Fire-conforming APIs. That's sort of our bread and butter. Well, what's new and novel is we're now adding this enrichment layer. When the data comes into our platform, we work with West Coast Informatics to use their auto mapping tool. We productize that, and as the data flows in, we're now taking the contents of those Fire resources, comparing them against the AI model and getting back the SNOMED or the CPT or the LOINC codes, updating the Fire records with those results, and putting that back in our repository to give you more high-quality, optimized, computable data, right? And that in itself offers value to our customers who want to use that to drive their own applications or their own decision support or analytics. But we also, within Smile, are using this for our own innovative product development. And this is the next layer of our stack, which is the clinical reasoning layer. We want to write those CQL rules that I showed you earlier. We want to write digital quality measures and find care gaps and do clinical decision support using the clinical quality language standard, or CQL. But we're dependent upon high quality data to achieve that outcome. Right now that we have that built into our platform, our tools around clinical reasoning will be much more effective and they'll give much better results. And then the last layer of our stack is we are also building tools that allow our customers to be compliant with government regulations like the CMS mandates that are coming out or have been out, and the next generation of them are coming out in 2027. That requires that you do things like automated prior authorization transactions between payers and providers, and Fire-conforming exchange APIs and exchange mechanisms. And all of that will benefit, again, from having high-quality standardized data and having the outcome of our clinical reasoning engine to feed into that. So in summary, not only is this really important for Avery as the patient, obviously she's going to get better care, we're going to intervene earlier, we're hopefully going to give her a better health outcome. But the providers themselves will be able to make better decisions, the researchers will have access to better standardized computable data for their purposes, governments who want to do population health studies will have access to this as well. There's a whole host of stakeholders that we believe can truly benefit from high quality data, of which semantic standardization is a key component in achieving that vision. So Brian, with that, I think we'll wrap it up.
Yeah.
Last words?
No, without doing this, you can't use the data as effectively as you can if you do this. And that's really the bottom line for all of the different ways you might want to use it.
All right. We saved 2 minutes for questions, so thank you. Anybody have questions? Here.
I'm an engineer, but not in healthcare. So I'm asking a question that might be already known. Where does the ontology for your semantic representation fit in? Is that the Fire standard or is it something else?
Yeah, I mean, in the Fire standard, there is a definition for a set of terminology services. And so part of this is having access to the ontologies that underlie the standards as part of the ecosystem so that they can be queried and resolved against as part of the way of doing this. Yeah. So that data is included in the solution. Yeah.
Any other questions? All right, well, if not, come visit us at the Smile booth. We're just directly behind, conveniently located, 20 feet away. Happy to give you demos or answer any questions or have a discussion about this topic. Hope to see you there, and thank you.